Hi everybody, this is Jim Corkins again, and we are at the final part of our journey through kinematics. And again, this is continuing on with projectile motion, and now we're going to combine what we learned in 1.51 and 1.52 to this final part, which is where something is launched from a height and it has a launch angle to it. So it's going to be launched from a height, or it's going to be launched from the ground up to a height at a launch angle. So the reverses happens too. So you should be finishing up your homework at this point, and you should have finished the reading at this point. So if you haven't done those, please start working through those. Okay. Well, again, just to remind you, here is the essential strategy that we're going to take when we're going to be solving these problems. We're going to make a pictorial representation for the y versus x axis to help us model how to do the problem. We're going to then list out our knowns and unknowns, and then we're going to use our equations of motion. All right, and then unify them by solving for the time of flight. And then after we do that, we're going to try to see if our answer kind of makes sense. Okay? So an object that is launched at a height and also a launch angle can be launched above the horizontal, 45 degrees above the horizontal, or below a horizontal, right? And in this case, it's going to go up in the air, and then it's going to be coming down. And again, this is a parabola problem right to this point, right? So it's just following a parabola. When it gets to this point now, it's reached its original height that it was being launched at. And now it's traveling down at that same velocity that it was being launched up at. But then it's going to keep speeding up past from there. So at this point, right here, it's coming down at 45 degrees at this initial velocity just in the opposite direction. But now it's going to be speeding up past that point. So in a way, when you've launched it up at that angle and now it's coming down, well, now it's doing essentially this right here. Okay, so when you're launching it up at this angle, it comes down and it's now getting to this point. And it's now coming down at that 45-degree angle, okay? Well, then it's just this problem right there. So in this case, it really doesn't matter what you do as far as you launch it, but you just have to kind of make sure, again, you're going to be doing in 5.2 when we had to launch it from triangles. Sorry, I'm moving all over the place. Oh, you had to break up the initial launch vector into VIY and VIX, and then you had to then go ahead and list your knowns and unknowns and do the solving problem. So there's going to be, again, from 1.52, we're going to be, when we're first given this initial launch velocity and angle, we're going to have to break those up in the x and y directions, and then we start doing the problem. But of course, you're going to graph out the problem, or you're going to do a y versus x graph, and to try to take whatever narrative they give you and put it into a graphical representation. But it's going to take a format of one of these two types of problems. Okay? So now that we have everything is coming together, now we can't assume that its initial initial height is going to be caught at the final height. In fact, it's going to be falling below its launch height, which is going to now have a negative height to it. Okay? And most likely, if an object is launched from a height above the ground, it's probably going to be launched at an upward angle, so that's going to be an initial velocity in the y direction. And it'll probably be like that VIY will probably be something like VI sine of theta. Okay? And since it's going to be falling below the horizontal, it's going to be falling below, we can't assume the final velocity is equal to the initial velocity, just negative anymore, because it's going to be speeding up past its initial velocity and then continue to speed up further. Okay. Since it is being launched at an angle, it'll probably be launched at something like this: initial velocity cosine of theta. It still will be moving at a constant velocity in the x direction, but it's going to be a little bit more of a complicated problem. Okay. So probably the best thing to do is to take a problem and just do it. Let's just do a problem, and that way you kind of get a feel of how to put parts 1.51 and 1.52 together, what we're trying to do now. So what we're going to do is we're going to stip, and we're going to do the shot putter problem, but now she's launching it from the shot put from a height of 1.8 meters. Okay? And we're going to go to our whiteboard. And we're going to paste our problem in just like we've done before. And now we're going to do it. Okay, so the first step in our procedure is to graph out the narrative here, right? So we have a shot putter that is going to be throwing a shot put, and this is positive y, and this is positive x. And she's going to be throwing a shot put at an angle of 40 degrees. So this is 12 meters per second is the initial velocity. And it's going to be an angle of theta, right? And she's 1.8 meters above the ground. So this is a height of 1.8 meters. Okay. And we're going to call this 0 meters. Rather, maybe we should do it from her perspective. Maybe we should call this 0 meters, and it's going to fall below her and a negative 1.8 meters. Yeah, that's what we'll do. And then it's going to come out here to a distance. So when this thing gets launched, it's going to come out, and then it's going to drop down here. Okay, so that means it's going to travel a distance here. I'm going to zoom in a squidge so I could put more detail to this. Negative 1.8 meters. It's going to be coming down at some final velocity and at some angle theta, which we don't know. We know this angle up here, which is going to be 40 degrees. All right. And it's going to land here at a distance xf, which is equal to delta x. And xi is equal to 0. And let's come over here. We're going to call this yi, which is equal to 0. And this is yf, which is 1.8 meters below her, which is actually delta x, delta y. Okay. So here's what we're going to do. We're going to treat this just like we did the problem that we did in 1.52. The only difference is we can't call delta y 0. We're just going to call delta y like a negative 1.8 meters, right? So let's go ahead and do this. All right. The the first thing that we have to do is we have to break up this triangle here at the top. And I'm going to draw it a little bit more detailed. It's being launched up, and this is at 12 meters per second. And this is an angle of 40 degrees. Well, the x direction is VIX, which is equal to VI, which is 12 meters per second cosine of 40 degrees. The y direction component is upwards, which is positive 12 meters per second sine of 40 degrees. Okay? All right. Well, we've got it pretty much graphed out, and we have all of our variables listed on here. Let's go ahead and we need to find, now we're going to need to find how far the shot travels. We need to find what delta x is. So we need to find what delta x is. And really, again, we need to find out what delta t is. So let's list out our knowns and unknowns here. All right. Well, in the delta x, so delta x is what we're trying to find. And we don't know that. We know VIX is equal to positive 12 meters per second cosine of 40 degrees. And while I'm here, I'm just going to actually get the number for that to make it easier on myself. 12 meters per second times 40 degrees, and that's cosine, equals 9.19. So this is just, it's being launched up at a positive 9.19 meters per second. All right. And it launched to the right at 9.19 meters per second. And all right, so that's pretty much all of our x direction stuff. Our y direction stuff we're going to do over here. Our y direction stuff, delta y, it's going to be falling below the person a height 1.8 meters. Okay. VIY, its initial launch angle is going to be positive 12, so it's being launched up at 12 meters per second, sine of 40 degrees. And again, while I'm here, I'm just going to do that. It'll be 12 times 40 degrees. Whoops. 12 times 40 degrees, which is going to be sine, equals 7.713. Okay. 7.713 meters per second. All right. Well, gravity is pulling down on it, so gravity is down, and that's negative 9.8 meters per second squared, or meters per second for every second. All right. That's pretty much all the variables that we have. There's no acceleration in the x direction, but we don't know, in order to get delta x, we're going to be using this equation right here. That means we need to know delta t. So again, our main objective, our secret main objective, is to get the time of flight, right? So the time it takes for it to travel from here to here is the same time it takes for it to travel up, come to a stop, and then fall down. Okay? So let's use this side to get our t equation, our delta t. Now, in our last problem, if I could show that to you, in our last problem, we had the option to use two methods, right? We used the y versus t curve fit, and we had to use quadratic equation to solve it for delta t, but we could have also used, since this was a uniform motion, we could have used this part here to actually solve for delta t too. You can't do this with our current problem because the initial velocity coming in it's not taking a perfect parabola. It's actually speeding up past its initial velocity. Right? So it's not over here. We could have done it if it was landing right here, but now it's speeding up past that, so the final velocity is not equal to the initial velocity. Oh, the final speed is not equal to the initial speed. So we have to do that quadratic stuff. Basically, this is what I'm saying. We have to use that quadratic equation stuff, which means delta y, which is equal to negative 1.8 meters, is equal to VI y delta t minus 1/2 g delta t squared, right? Well, this is this delta y we're going to bring onto the other side, so it's going to be 0 is equal to negative delta y plus our VIY t, which is 7.713 meters per second, delta t, and this part is just g over 2 delta t squared. It's a g. Okay, so basically if delta y is negative, so this is going to be 1.8 meters, it's a negative of a negative, plus 7.713 meters per second delta t minus 9.8 divided by 2, which is negative 4.9 meters per second squared delta t squared. So again, this is going to fall into C. Positive 7.713 is going to be our B, and negative 4.9 is going to be our A. So we're going to be doing negative b plus or minus square root of b squared minus 4ac over 2a. And we're going to be using this because this delta t is going to be this variable that we're solving for. Okay? It's a quadratic problem, and we can't use the other one to do it. All right. Here we go. Let's put in our numbers. So this is going to be negative. So we're going to put in, it's going to be negative b, which is going to be negative 7.713 is going to be that. Plus or minus, and it's going to be the 7.713. It's going to be squared minus 4, and that's going to be times a, which is negative 4.9, and then times c, which is 1.8. And I don't know why I put the meters there. I'm going to erase that. Just rewrite that all together. It'll look a little bit better. It is going to be 1.8. All right. Divide that by 2, and that's times a, which is negative 4.9. All right. Let's do this. So I'm getting two numbers. I'm getting positive 1.78 or a negative 0.206, and those are seconds, right? Well, time cannot go backwards, so this has to be the answer. Okay, 1.78, which makes sense, right? Our last time when we had 0 here for the height, it worked out to be a less time. So since we're adding that height to it, it's a little bit more of a time of flight, okay? So you should have gotten 1.78 or negative 2.06 in your calculators, okay? Well, now let's finish this up. We're going to have to go ahead and put in how far it went, okay? So delta x is going to be equal to VIX delta t, and VIX we worked out to be 9.19, well, positive 9.19 meters per second, and delta t is 1.78 seconds. And let's do our calculator here. 9.19 times 1.78. 16.336. 16.36. So this is going to work out to be 16.36 meters. And that's how far it went in the x direction. And that's what they asked us to solve. Let's actually take this a little bit further, shall we? Since we know the time of flight, let's do an extension of this problem. Let's say they also asked what the velocity incoming to the ground is and what that angle theta is, okay? So let's say they also asked what the overall velocity is, v final is, and also what theta is. Because that's typically another type of problem, is they'll also ask you the velocity that it's coming in at the ground at, and that the overall theta is. Okay? So let's go ahead and try it. Okay? Well, we have the time of flight. To get the overall final velocity in the x direction, to get the overall final velocity, we're going to need to get the overall final velocity is going to be coming down at final velocity here. It's going to have a y direction component down, v final y, but it's going to have its constant velocity in the x direction, which is VIX, which is equal to v final x. So to get that overall velocity, we need to know Vx, v final x, which is Vix squared, plus v final y squared. So that means we already know v initial x, which is 9.19 meters per second. We just need to find the final velocity in the y direction to get the overall velocity. And then we'll solve for the theta by using tangent of these two numbers. So how do we get the final velocity in the y direction? Okay, well, v final y is equal, and it's coming down, is equal to v initial y minus g delta t, right? And I'll just put a little minus there just to be consistent. So this velocity in the y direction we know is going to be negative because it's coming down, right? But we'll let the math work it out. Well, the initial velocity up in the y direction we figured out earlier, and that was 7.713 meters per second. And we know g, which is just 9.8 meters per second squared. We put the vector in front in the equation. And delta t, the total time of flight, was 1.78 meters, 1.78 seconds. Okay, so v final y is going to be equal to, let's do a little bit of math here. This will be 7.713 7.713 minus 9.8 times 1.78 in parentheses and enter. So negative, so that velocity is negative 9.731. Negative 9.73 meters per second downwards. So it worked itself. There we go. So now we could actually figure out what this is, right? Since we have both of those, we could find out the overall velocity. And since we have those two things, we could also find out what theta is. All right? So let's figure out the overall velocity. The overall velocity that it's coming down at, by the way, we're solving for this velocity that's hitting the ground at and that angle that is hitting the ground at, is going to be equal to the v final y squared velocity plus the v final x squared velocity. We know the x squared velocity, which is the initial velocity, which is 9.19, and we now know this. So now we're going to square root, and we know the v final y. So now we're going to square root those guys. Negative 9.73 meters per second. We're going to square that, plus the 9.19 meters per second squared. And so let's find out what that is. So we're going to multiply that by itself. Actually, we could have just squared it. Back. 9.73 and square 94.67 plus we're going to do the 9.19 and then we're going to square that and then parentheses that and add those two together. Now we get 179.19, so that's what this is, and then we need to square root that. So it's going to be hitting the ground at 13.38 meters per second. Okay, so now we know that it's going to be coming down at, it's going to be hitting the ground up here at 13.38 meters per second, right? And we could figure out that angle now because we have this v final y, which is negative 9.73 meters per second. We could figure out theta, just do the inverse tangent, right? So that theta is going to be the inverse tangent. Actually, we could use inverse sine or inverse cosine since we have the hypotenuse here. And that, again, is 13.38 meters per second as coming down out. Anyways, let's just do this right here. So this is going to be negative 9.73 divided by 9.19. All right. So 9.73, just put in negative, divided by 9.19. You could just put you don't have to put the negative in there. Equals, and we're going to do the inverse tangent of that. Boy, that's Okay, 9.73 divided by 9.19 equals, and we're going to do the inverse tangent. So it's coming in at an angle of 46.82 degrees as well. Okay. So in these problems, they'll typically ask you a multi-part problem just like this. They'll ask you to find out how far it goes. They may ask you to find its final velocity, its overall final velocity, and also the angle that it's coming in at. So this is essentially how to do this type of problem. Okay. And we basically covered all these other problems too in that. This is like a quick guide to what we just did with the equations. Essentially, what you're going to have to do is merge some of these equations together. But I kind of like just what we did is just try to use logic and just think about it. Don't try to adhere to memorizing equations. Try to actually really think about the problem and graph it out and follow the procedure that we did, right? So that procedure was to make a graphical representation of what is being asked, okay? And then we graphed it out. We try to put in our variables here. We then listed, given that we knew that launch angle, we would have to find the velocity in the x direction and the initial velocity in the y direction. Once we found those, we listed out our knowns and unknowns, and then listed out what we need to do. Again, you're going to need to find the time of flight. So first thing you do in these problems is solve for the time of flight, which is what we did. In this case, we had to use the quadratic equation to do it, and that's how we got the time. And then we use that to get the range, how far it went in the x direction. Okay. And then we just did a little bit of an addition. We added. So that's what was being asked. But then I added this part. How do you get the overall final velocity right before hitting the ground and the angle it's hitting the ground? In order to do that, we had to find the final velocity in the y direction. We already knew the velocity, the final velocity in the x direction, which was equal to its initial velocity in the x direction. And then we solved for the final velocity in the y direction using the linear fit. And now that we had that time of flight, we knew we could use that to find the ending final velocity. And then we put that back into this Pythagorean's theorem to solve for that hypotenuse and found out that. And then we used the y direction and the x direction to find the angle at which it's coming in. But since we found the hypotenuse, we could have used inverse sine or inverse cosine too. Okay? So I hope you learned a lot, all right? And this concludes kinematic equations in 1 and 2 dimensions. All right, bye.